going to start the lectures section. For me, it's a great pleasure to introduce Professor José Antonio Gálvez, da Universidade de Granada, that is a close friend of Brazil and interchanging geometric researches with many Brazilian people. So welcome here. And he's going to talk on uniqueness and immersed surfaces in threemanifolds in the conjecture by Alexandrov.
Thank you very much. First, I would like to thank the organizers for giving me the opportunity to talk here. I'm going to talk about a joint result with Pablo Mira. And in this talk, we have two objectives. The first objective is to obtain a general Hopf type result. Remember that the classical Hopf theorem says that the unique constant mean curvature sphere, immersed sphere, in the Euclidean space are the round spheres. Our objective is to obtain a general, in some sense, a very general result in this way. For that, we are going to consider, instead of R3, the Euclidean space, as Hopf did in this result, an arbitrary three-manifold M. We change the equation, CMC equation, and we substitute this equation for a general elliptic PDE. And we want to, in the Hopf theorem, say that the unique sphere are round sphere. So we change round sphere for some candidate surfaces in the general context. So in order to be more concrete, let us start with a class of immersed-oriented surfaces in a general three-manifold, arbitrary three-manifold. Suppose that the class of immersed-oriented sphere are the solutions of a certain second-order elliptic PDE. And in this general class, we choose a subset of this class, a certain family that we call the candidate surfaces, such that these surfaces foliate the Grassmannian, the oriented Grassmannian of the manifold. This means that when in the manifold M we consider a plane, oriented plane, we only have one surface in our family such that it is tangent to that plane at the corresponding point. So in these conditions, I will explain that it is very general. Any immersed sphere of the class must be necessarily a candidate sphere here. Observe that if we consider in the Hopf theorem, the class of immersed-oriented surfaces is all the constant mean curvature surfaces. The elliptic PDE that it is used here is the PDE associated to CMC. And the candidate surfaces here are the spheres. When you move a sphere, when you consider a sphere of a certain radius, if you consider a plane, an oriented plane in R3, there is only a translation of this sphere that it is tangent, well, it is tangent to this plane at that point. Okay? So this is in the case that we consider as elliptic PDE CMC equation and the candidate surface is given by the round sphere of a certain radius, we recover the Hopf theorem. But This result, it is not only for CMC sphere. Observe, for instance, in R3, if we consider, instead of CMC surfaces, we consider constant Gaussian curvature, positive constant Gaussian curvature. This is an elliptic PDE. As candidate surfaces can be used also round spheres, and the result says that the only surface in R3 with immersed sphere in R3 with constant Gaussian curvature, positive constant Gaussian curvature, must be a round sphere. This is the classical Liebman result. Okay? But this result can be used in a very general way. Observe that the manifold is not R3. It is a general manifold. Okay, in order to understand what means this of candidate surfaces, I'm going to give some examples. In R3, we are saying that for order to be a candidate family, we need that for every oriented plane, we need that an element of the candidate family is tangent, and only one is tangent to that plane. For instance, if we consider an ovaloid, in general, an ovaloid in R3 S, and we consider all the translations in R3 of this ovaloid, we obtain a candidate family, because given a plane here, there is only one and a point, of course. There is only a translation of this ovaloid that it is tangent at that point with the same normal. Okay? This is a sample of a candidate family in R3. Other examples, for instance, are planes in R3, this is obvious, or horospheres in H3, and also in general in space form, round sphere with a fixed radius. Also, it is possible to obtain other different kind of candidate surfaces families. For instance, if we have a disk, we consider the cylinder over that disk, and we consider a rotational surface around this that it is tangent to the cylinder. If we consider this surface as this cylinder, the reflection, and we consider all the translations of these three surfaces, we obtain also a candidate family for a certain problem. But this construction is in space forms, but in general, similar construction to this kind, to 1, 2, or 3, are possible when we consider M as a homogeneous three-manifold. This is possible in general. Observe that in our theorem, we say that if we consider an immersed sphere in the class, the surface must be in the candidate surfaces. But if in our case we don't have observed here that here the family of candidate surfaces has no sphere here. So the previous result said that in this family there is no sphere. So it can be understood also as a non-existent result. Okay, consider for instance as a simply connected homogeneous three-manifold. It is well known that the dimension of the group of isometries of M can be 6, 4, or 3. In the case of the dimension is 6, it's a space form. If the dimension is 4, we have the space E kappa tau. They were defined by Laurent. And in general, when the dimension is 3, we have a general Lie group with a left invariant metric. A central result in these spaces, in E kappa tau spaces, is the famous result by Average and Rosenberg. It asserts that CMC spheres in a I kappa tau space must be rotational spheres. In these spaces, all of them have rotations. So it is possible, in this case, to construct a rotational example in the following way. Now, we can extend this result in the following way. Consider a general relation between the mean curvature, the Gaussian curvature, and the extrinsic curvature. So, if there is a relation of this type, and the W, the relation is an elliptic equation, we obtain in a very general elliptic equation that any sphere in a space I kappa tau satisfying this equation must be, in fact, rotational. The key point here is to obtain, to be able to obtain a rotational example and prove that the rotational examples are, in fact, candidate examples in this case. And using the general result, we obtain uniqueness of surfaces satisfying these relations. Okay, but it is important to assert that the result is, can be used, of course, for generalize some previous result given in a space form, but it gives also some interesting result in in the Euclidean space, in fact. For instance, there is a result by 1 and 1 that asserts that if you consider, in R3, you consider the sphere, the unit sphere, and you consider a certain function on the sphere, a positive C2 function on the sphere satisfying that the value at a point and its antipodal point is the same. So there is only a unique ovaloid satisfying that for every point P with normal eta, its mean curvature is given, the mean curvature at this point is given by the function h at the corresponding normal. Okay? Observe that this equation, this is the CMC equation equal to this. This equation is elliptic. So we can use the general result and assert that this ovaloid constructed by 1 and 1 is, in fact, the unique ovaloid immersed in R3 satisfying these conditions. So we obtain the uniqueness of for the theorem of 1 and 1. The uniqueness was only known if the immersed sphere, observe that we've proved that any immersed sphere satisfying this condition about the mean curvature, the result was known for a general sigma only when sigma, in fact, was another ovaloid. The second objective of the talk is an Alexandrov, a conjecture by Alexandrov related with the previous problem in the same way. Consider a surface in R3. We say that the surface satisfies a prescribed curvature equation if there is a relation between the biggest principal curvature, the lowest principal curvature, and the normal of the surface. We will assume that the relation is C1. Okay? Then the ellipticity condition of the equation is say that the derivative with respect to k1 and times the derivative with respect to k2 is positive. Observe that we assume that this functional is c1 with respect to k1 and k2, but not possibly is not continuous with respect to the normal. Okay, in general, this equation has been very studied, and for instance, some examples of this case are when the functional does not depend on the unit normal. These surfaces are called surfaces, Weingarten surfaces. In the case that a Christoffel problem is also a problem in this case, when the sum of the curvature radii is equal to a certain function given by the normal, a positive, in fact, function depending. The classical Minkowski problem also lies in this case. The problem is to determine a ovaloid such that the Gaussian curvature is equal to a certain function depending on the unit normal. And also the prescribed mean curvature the problem is to describe the surfaces such that the mean curvature is a certain functional depending on the normal. The classification of a sphere of prescribed curvature have been deeply studied by different authors. For instance, this one, but of course for many others. And Alexandrov conjecture that this equation, in the general case, has at most one solution. In fact, we solve the conjecture, and I'm going to explain, and say the following. Assume that we have a surface S, that it is an ovaloid, okay, satisfying the prescribed curvature equation W equal to 0, where here W is not elliptic in general, but it is necessary that it is elliptic in certain region. Okay, the region depends on the principal curvature of the surface S. We have a surface S satisfying a certain relation, and the problem says that if we have another immersed sphere in R3 satisfying the same equation, elliptic equation in some point, then the new surface must be a translation of the first one. This problem was known, for instance, for Christoffel problem or the Minkowski problem. Okay. In fact, the theorem was known also when this second surface is also an ovaloid, but not in the general case. It is important to observe that in general this problem has no sense, or should be different if the first surface S here is not an ovaloid. If S is not an ovaloid, it is easy to find a sample of two different surfaces satisfying the same equation, but one is not the translation of the other. So it is crucial, the fact that S is an ovaloid. Here, as a consequence of this result, we obtain the classification of elliptic Weingarten surfaces in the Euclidean space. This problem has been studied for many authors, and we prove that given an immersed sphere in R3, if we assume that around each umbilical point, the surface satisfies a C1 relation around the umbilical points with the elliptic condition, then the surface is in fact a round sphere. This problem was known when sigma is embedded using reflection principle by Alexandrov. It is possible to solve this problem when sigma is embedded. If the surface sigma is real analytic, it was proved by Vos that the result is also true. It was also true, known that it was true when the functional W is symmetric. Observe that this is the biggest principal curvature and this is the lowest one. When it is symmetric, it was proven by Hartmann and Wigner. But observe that very simple cases like this equation, observe that this equation is elliptic, and it is clear that the unit sphere satisfies this equation. But it was not known if the unit sphere was the unique sphere satisfying this equation. As a consequence, we obtain that it is true. Okay, I'm going to talk about the proof of the general uniqueness theorem. Okay, let us start explaining what is the meaning of a class of surfaces modeled by an elliptic PDE. We are going to consider, for a general manifold M, I'm going to consider the Grassmannian of, the planes, the oriented planes, the Grassmannian oriented plane, that means that given a point and a normal, given a point P and a normal, we consider the element corresponding to the tangent of, at this point, to this normal. Okay. So, given a plane, we are going to associate to this plane, associated to this plane, we are going to consider a second order elliptic PDE around this. Around this, we will have the solutions of this elliptic PDE. Okay. And okay. We consider elliptic PDE, and we will assume that the PDE is elliptic. The condition of being elliptic is these two conditions. Okay. We say that a class of surfaces is modeled by an elliptic PDE if the elements of the class or the surface of A are exactly the solutions of the PDE, at least locally. For instance, if we consider CMC in a general ambient space, if we consider the CMC equation, A is in fact the set of all the CMC surfaces in the ambient. Okay? So this is the meaning of being modeled by an elliptic PDE. So the result asserts that if A is a class of oriented surfaces, and we assume that A is modeled by an elliptic PDE, and there exists a family whose tangent planes foliate the oriented Grassmannian of plane of M. This means that for every plane, at every point, we have only one surface on our subset S that it is tangent at that point. And when we move in the point, the surface also moves smoothly. Then every sphere in the general class must be a candidate sphere. That is, every sphere of the class A must belong to the subset S, necessarily. As I said previously, you can imagine, in order to understand the meaning of the result, that A are CMC surfaces, and these candidate surfaces can be spheres, the sphere of a certain radius. So the result asserts that every CMC surface in the class is a round sphere. Well, I'm going to give a sketch of the proof. It is as follows. We are going to consider a surface, sigma, we will consider on sigma the second fundamental form of sigma, and for every point P in sigma, we consider the only candidate surface that it is a tangent at that point. So here we consider a candidate surface at that point. We consider here the second fundamental form of this candidate surface. I'm going to call gamma. And now we define the difference between the second fundamental form of my surface and the second fundamental form of the candidate surface. Of course, observe that the candidate surface is different at every point in general. Here we can have another different candidate surface at different points. So we define the difference between both of them. In the case of CMC surfaces in R3, what it is the candidate surfaces are spheres, and it is satisfied that the second fundamental form is a constant, the mean curvature times the first fundamental form. And for a general surface sigma, the second fundamental form, this is the candidate, excuse me. The second fundamental form of sigma in a conformal parameter, for instance, is given by the Hopf differential plus H1 plus the conjugate. So sigma in this case, in this easy case, is simply the Hopf differential minus the conjugate. Okay? But in general, it's much more complicated. Okay. Okay, in this situation, it is obvious that sigma vanishes identically on every candidate surface. This is obvious because the second fundamental form and gamma is the same in that case. Now, observe that the difference vanishes. These terms are computed using second derivatives. So these two terms agree when the surface sigma and the candidate has a contact of order at least 2. This is obvious. Okay. Okay. The idea of the proof is to show that sigma is set at the point where sigma vanishes is a Lorentzian metric on our sphere, immersed sphere. And the null direction of the Lorentzian metric have isolated zeros of negative index. So Poincaré-Hopf in the theorem would say that it is impossible. Okay, in order to understand the proof, we are going to do the following. Consider our surface sigma and consider the candidate surface here at a certain point Q in sigma S. And now we are going to study the difference between the second fundamental form of sigma and the second fundamental form, minus lambda. So for that, we consider local coordinates here, local coordinates, and we do the following. Sigma at this point is the difference between the second fundamental form of sigma and the second fundamental form of this surface, this candidate surface at this point. Okay, sigma is this difference. In order to do some computation, we are going to do the following. We consider the second fundamental form of our surface minus the second fundamental form of at this corresponding point at S. I'm going to explain what is the meaning of this. Plus the second fundamental form of S, that it is a candidate surface, minus gamma, where gamma is here the second fundamental form of this second candidate surface. Here we are considering in certain coordinates the matrix corresponding. When I write sigma, I want to say sigma with respect to partial u. When the surface can be, as the surface can be seen as graphs, so we consider coordinate in the ambient space uv and the height. I'm indicating saying that this is this quantity. This is the same here, partial v. Okay. And we are going to estimate, to compute, to do some computation for this difference and this other difference. Okay. We consider the local parameters uv and the height. We can parameterize, of course, the surface S and the surface sigma in this way, u as a graph. uv and the height is h, and for S, this is psi naught, the height is h naught. Okay, for a general graph, the symbols of the second fundamental form, for instance, E, the second fundamental form with respect to partial u, this is E. Okay, for a general graph. This can be computed as a certain function depending on u, v, h, the gradient of f, the gradient of f, and f, u. For every graph, not only for our surfaces, but in general. So, if this is true, it basically using the mean value theorem, we can prove that the difference between the second fundamental form of psi and psi naught around the origin is given by this expression of this kind. Observe that they depend on f, fu, fv, and fuu. So we obtain a expression of this time, where these functions are smooth in a neighborhood of the origin. Similar formulas can be given for f and g, the other coefficient. This is f and this is g, the other coefficients of the second fundamental form. Okay, so as both graph h and h naught are solutions of the same PDE, C1 alpha elliptic PDE, we can use the classical Bird theorem that asserts that the difference has a first homogeneous polynomial, and it is harmonic. I mean, the difference is a homogeneous harmonic polynomial plus high-order terms. So the behavior of this is more or less as a harmonic polynomial. Okay, so if we come back to this expression using that the difference is controlled by P, the less order term is here. The difference depends on the second derivative of the difference between H and H naught. So the first term is dominated by PU. So doing the same for the rest of terms, we obtain that the difference between the second fundamental form of our surface sigma and the second fundamental form of the candidate surface at this point is controlled by the Hessian of the homogeneous harmonic polynomial P plus, and we have a high order term plus other terms. For the blue part, we have divided the control of this expression in terms of two sums. So for this quantity, in a similar way, we can prove that the difference has the order of this term. So we finally obtain that if sigma, the difference between the second fundamental form and the second fundamental form of the candidate's surfaces at each point does not vanish identically, we have that sigma is the Hessian of a harmonic homogeneous polynomial plus other term of higher order. Observe that sigma, obviously, because sigma is harmonic, this metric is Lorentzian. The sum is equal to 0, so it is Lorentzian. If sigma does not vanish identically, sigma is a Lorentzian metric and has isolated singularities. This is due to the fact that the polynomial is harmonic. And also the fact that the fact of harmonicity of P gives that the index of the null line fields of sigma, the index is negative at every singularity. So the Poincaré-Hopf theorem, index theorem, asserts that this is impossible unless sigma vanish identically. If sigma vanish identically, we are saying that sigma is a candidate sphere. So this is more or less the main ideas of the proof. Okay, now I'm going to talk about the second objective. The second objective is the Alexandrov conjecture. We start with the novaloid S in the Euclidean 3 space, satisfying a prescribed curvature equation, W. We assume that W is C1, okay, in K1 and K2 at no regularity in N. But the ellipticity condition is only satisfied in some points. Observe, for instance, that if S is a sphere, this set is exactly the umbilical points. The umbilical points for the new the set where the ellipticity condition is satisfied is exactly where we have umbilical points, but it is not in general this set. Okay, now we assume that there is another immersed sphere, sigma, in the Euclidean space, satisfying the same equation. So we want to show that sigma is a translation of the first ovaloid. Well, here we have two main difficulties. The difficulties come from the fact that the ellipticity condition is not global. the ellipticity condition is not satisfied on the whole surface sigma, only at some points of sigma. On the other hand, the equation 3 is not C1 alpha, but in fact is probably is elliptic, but it is not, the coefficients are not continuous, because K1 and K2, when we reascribe in terms of the mean curvature, Gaussian curvature, these two terms appear some square roots, and we don't have any control about the equation. We don't know if the coefficients in the equation are in fact continuous when we write in local coordinates. For that, we are going to use a classical transformation given by the Legendre transform of a surface. The Legendre transform of a surface can be defined when the surface has a curvature different from 0, and if we assume that it is tangent at the origin with a tangent at the origin to the plane theta z equal to 0, the Legendre transform of our surface will be given in this form. Eta are the coordinates of the normal in R3. This transform has good properties in terms of the normal. Observe that our condition talks about the unit normal of our surface. And here, observe that the unit normal of this transformation, this new surface, this is our initial surface. We consider a transformation of our surface, okay? And we consider a usual coordinate. I'm going to explain. We have our surface. Psi, and we consider the Legendre transformation of this surface, and here we consider usual coordinates xy. In this coordinate, observe that xy basically are basically the unit normal of our surface. It's a way to do some computation of our surface in terms of the unit normal, in some sense. Okay, in this case, the unit normal is given in this easy way. The second fundamental form of this surface satisfies that it is given by this times the Hessian of the height of the Legendre transformation. H is the height of the Legendre transformation, and it is important that the principal curvatures of our initial surface is only a certain function of xy, the coordinates, and only the second derivative of h. This is a key point. Now, the second step of the proof is to consider the elliptic PDE associated to this coordinate xy. Consider a point on our surface sigma such that the difference between the second fundamental form, a point P, where the difference between the second fundamental form of the surface minus the second fundamental form of the initial surface is the ovaloid, when we translate to that point, is equal to 0. Assume that we have a contact of order at least 2. Okay, in these conditions, we consider the Legendre transforms of our surface sigma and also the transform of S. And using that, we have the same equation, W of K1, K2, and eta equal to 0, we can rewrite everything in terms of the xy coordinates, and we obtain that the difference between the heights of the transforms satisfies this equation. It is important here to observe that this equation is uniformly elliptic, but the coefficients probably are not continuous. Okay? As a consequence of a result by Beers and Nirenberg, in these conditions, when the equation does not depend on terms of first order, you have that the zeros of rho are of finite order. This means that if you have a rho, the function rho, some derivative of rho, some derivative is different from 0, except that a smooth surface can have all of its derivatives at a point, at a fixed point, equal to 0. All the derivatives equal to 0, but the function is not 0. Okay? What Beers-Nirenberg theorem asserts is that some derivative of rho at the origin must be different from 0. And in fact, also asserts that the first derivative of rho with respect to x or respect to y have no interior extrema. Okay, using that, now we are going to prove that sigma has isolated zeros of non-positive index. Here it is impossible for us to prove that the index is negative, but in this case that it is non-positive. So this will be enough. Okay. Define again the difference between the second fundamental form of our surface and the candidate surface S. It is important here to observe that S is an ovaloid. So both principal curvature, we can assume that both principal curvature are positive. So the second fundamental form is in fact a Riemannian metric. This is a key point. Okay, now consider the point P where sigma vanishes, but it's not identically equal to 0 around P. Then a simple computation gives that, as a consequence of the previous comments, that sigma is basically the Hessian of rho. But we have some property about rho. Rho, if we consider the first polynomial in the series defining rho, W, using that the uniform ellipticity, we obtain that this homogeneous polynomial can be written as a polynomial with no zeros and times a product of linear combination where the exponents here are necessarily equal to 1. This is the consequence of the fact that the ellipticity is uniform, that these coefficients are equal to 1. If this is true, it is not difficult to prove that then W satisfies that the determinant of its Hessian is negative around the origin. Well, so if this is true, so rho is controlled by W, by this polynomial. This polynomial satisfies this condition, so rho around the origin also satisfies this condition. So sigma is in fact, because the fact that the determinant is different, is negative, is a Lorentzian metric with an isolated singularity at the point P, because it is the determinant is in fact negative in the domain around 0, the puncture domain. So it is easy to prove. It is an elementary result that the index of the null lines corresponding to sigma, because sigma is a Lorentzian metric, we have two different null lines. The index of the null lines of sigma at the origin is non-positive if and only if the index of the gradient as a vector is around the origin is non-positive. Once we have proven that, we obtain that the index of the gradient is in fact non-positive. Why? Because Bers-Nirenberg result asserts that rho x has no local extrema. In particular, the origin is a saddle point of this function. So it is classical that if you have a saddle point, the index is non-positive. So we have that the null line of sigma have isolated singularities of index non-positive. But here we are not finished the proof. Why? Because our surface is not necessarily convex. We are comparing the surface at a point with positive curvature with S. And we can say that we have a well-defined tensor sigma around that point. But we cannot show that sigma is Lorentzian at this point. When the curvature is negative, sigma probably is not Lorentzian. Okay? So we are not finished at this point. But observe that here, when we have a contact of order 2, sigma has positive curvature as S. So in order to extend sigma, what we do is the following. As we commented previously, gamma is a Riemannian metric. Gamma is basically the second fundamental form of X. X is an ovaloid, so sigma is a Riemannian metric. So we can define a new tensor. The tensor is given in this way. Okay? Maybe sigma, as I'm saying, sigma is not Lorentzian at the point of non-positive curvature. So we define T, and we observe that T is proportional to the identity only when sigma is equal to 0. Only in these cases, using the ellipticity condition at the corresponding point, sigma can vanish only at the point where T is proportional to the identity. So T define eigenspaces L1 and L2 on a certain set where sigma is different from 0, but the set of points where sigma is different from 0 are isolated points. So the spaces associated to T are well defined globally, except at the point where sigma is equal to 0. Okay? But we have an important property here that around a point where sigma is equal to 0, if we want to compute the index, imagine that sigma is equal to 0 at that point. So we have that the null directions in a neighborhood, we have that the null directions of sigma satisfy that bisect with respect to the metric gamma to L1, L2. So the index of our of L1 and L2 agree with the index of sigma, of the null line of sigma. So now we obtain that the index of the eigenspace, the eigenspace at the isolated zeros of sigma is non-positive, because so it is the index of the null direction of sigma. So using again the Poincaré-Hopf index result, this is impossible if sigma is diffeomorphic to S2. So sigma, in fact, must be equal to 0, and the surface must be a translation of the initial surface S. In order to finish my talk, I wanted to say that there is a related open problem that probably is very difficult, but it is, in my opinion, very important, that if you consider a product space given by a space form cross R, and you consider the word metric f times the usual metric of the space form plus dt squared, the problem is to know if all the CMC spheres in this word space are in fact spheres of revolution. Obviously, this is true in the case that f is equal to constant, proved by Average and Harold, but it is not known in a general, at least for general functions f. I think it is an interesting problem in order to work in. So thank you very much for your attention.
Questions, comments?